Alright, welcome back. We're on part 2 now of our lecture about bringing air to saturation. And like I said, on the left side of the screen here, we're putting together a list of ways of bringing air parcels to saturation. And the first two have been kind of losers. I mean, they're fascinating. They just aren't how a thunderstorm works or a hurricane or something like that. We need a better way, a more efficient way to produce saturated air parcels so that we can get condensation and precipitation and snow and all that kind of stuff. And the big winner is going to be saturation by cooling. Remember, our best way to create saturated conditions was to cool the air parcel. That's because by Clausius-Clapeyron equation, that tells us that as we cool the air parcel, the saturation vapor pressure is going to go down. Well, since relative humidity is just vapor pressure divided by saturation vapor pressure, making the denominator, or bottom of that fraction, smaller, makes the relative humidity bigger. And eventually it'll hit 100%. Cooling air parcels is going to be our main way of producing saturation. Cooling the air parcel to its dew point. Remember, that's what dew point means. It is the temperature to which we cool an air parcel for it to become saturated. Okay, cooling, changing the temperature of air. Sounds good. How are we going to do that? Well, here we kind of fall back on some terminology that comes to us from the grim little science of thermodynamics, but it turns out to be important here. We're going to say that there are two different ways to change the temperature, well, of anything actually, but of air parcels in particular. And those are going to be diabatic processes, or diabatic cooling, and the opposite of them, adiabatic processes, or adiabatic cooling. Okay, let's look at that word real quick here. Diabatic, adiabatic. Okay, make sure that you can, well, I guess it's not critical that you can pronounce them, but make sure you recognize and have those words, because we're going to find out that they're very important. Really, we're going to be using words like diabatic and adiabatic for the rest of the semester. Let's talk about what those words actually mean. Let's talk about what it means for a temperature change to be diabatic. Okay, so this is the one that starts with D. Diabatic temperature changes. Oh, I'll take a definition that comes from one of the printings of your textbook. Diabatic temperature changes are temperature changes caused by adding or removing heat from an object. That sounds like a temperature change. Wait a minute, there's going to be an alternative to that? Yeah, there is. Diabatic temperature changes are where you literally are adding or removing heat from an object. This can be done by any of those kind of processes that we learned about back in the first module of the course. Things like emitting or absorbing radiation. Energy is actually being put into the object. That is a diabatic temperature change. Conduction. Remember, like when you put something cool onto a hot burner, when things are touching and heat is moving from the hotter object into the colder object. That is a diabatic temperature change. And diabatic temperature changes happen in the atmosphere. Lots of important ways and lots of important examples of temperature changes and possibly saturation happen due to diabatic temperature changes. The one your book throws around is what we call radiation fog. I love that term, radiation fog. It sounds like something that would happen in an old horror movie or something like that, like the beast from the Black Lagoon emerged from the radiation fog. Okay, it's nothing scary. Most fog that you experience in your day-to-day life is radiation fog. Radiation fog happens at night when the ground cools by emitting long-wave radiation. You know, that's why the ground cools. Hey, by the way, we could now use the word diabatic temperature change to describe what's happening to the ground. The ground is actually getting cooler because we are literally removing heat from it in the form of long-wave radiation. And then the air cools by touching the ground. Well, the air is warm, the ground is cold at night, therefore heat is removed from the air and put into the ground by conduction, which, by the way, is another example of a diabatic temperature change. We are literally removing heat from the air and putting it into the ground. That makes the temperature of the air fall. And, well, if we drop the temperature all the way to its dew point temperature, the air will become saturated, and we're going to need to start removing water vapor from the air parcel and converting it into liquid water. You know, those little liquid water drops might be fog, they might be dew. I mean, that's a detail that's hard to sort out exactly. But radiation fog is just that fog that results on this. All we did is just let the ground cool by radiation at night. The air touching the ground cooled by conduction, but all that's diabatic temperature changes. We're literally just moving heat around. Okay? That's an example of a diabatic temperature change. Other types of fog can do this too. It's a little more subtle, but for example, advection fog. Again, I don't want to get bogged down in your textbook's list of like 7 different kinds of fog. But advection fog happens when you move air from one place to another where the surface temperature will be different. For example, the most common example of advection fog happens when you take some warm, moist air, like maybe off the Gulf of Mexico or something like that, and you move it, you transport it, let's use a power vocabulary word, it advects. Remember, advection is moving something with the wind. Advects to some place where the ground is cooler. And when the air moves over this place where the ground is cooler, by conduction, heat will move out of the air and into the ground. That by a diabatic temperature change will cause the temperature of the air to fall. And if it falls all the way to the dew point, now your air is saturated and you're going to start getting fog, advection fog. This happens particularly often in the winter when there's like snowpack on the ground in some place, but not others. So like if a big snowstorm has come through and there's snow on the ground, okay, and then a different day some warm, moist air, maybe from the Gulf of Mexico or something, moves over, well, all of a sudden this relatively warm, moist air is moving over a place where the ground is cold, right? And so as a consequence, the air starts to cool by conduction, a diabatic temperature change, and you get condensation. Okay, another way in which you could get a type of fog, in this case it's an advection fog. Well, once you start thinking about this, these diabatic temperature changes seem pretty typical. I mean, actually, you wouldn't have come up with the word diabatic, but my guess is even before you took this course, you could have thought about how do you think you're going to change the temperature of air? I don't know, moving heat in and out of it. Sounds pretty good. In fact, it can be pretty hard to think that there actually are other ways this could happen. It's hard to imagine that there's something other than diabatic temperature changes, but there are. There are the adiabatic temperature changes. Here, this word A, this letter A at the beginning, is the prefix that means something like without. Okay? Adiabatic temperature changes are temperature changes that happen without adding or removing heat from the air parcel. Well, actually, any kind of object can have adiabatic temperature changes, just like it can have diabatic temperature changes. In this class, we're just talking about it in the context of air parcels. But wait a minute. How are we going to change the temperature of an air parcel without actually adding or removing heat? Turns out this is actually a big chunk of what the science of thermodynamics is all about. But in the context of like weather and so on, these things are going to mostly happen, these adiabatic temperature changes are mostly going to happen due to vertical motions in the atmosphere. Vertical motions are going to result in temperature changes without us actually having put any heat in or taken any heat out of an air parcel. And let me demonstrate how that's going to work. Alright, so here I have on this slide here, see this background here, I'm just kind of showing you like, height or whatever. And I've got some little ball here that's supposed to look like an air parcel down here near the surface, okay? Again, remember, air parcels are just sort of an idea. The air isn't really made of air parcels, but we can do things and we can think about the air problems in the atmosphere using an air parcel. So let's start with an air parcel down near the surface. Let's give it some pressure, let's say 1,000 millibars. That's a pretty typical pressure near the surface of the Earth. And let's give it a typical temperature, let's just say 30 degrees Celsius. Okay, great. This air parcel has a pressure of 1,000 millibars. The air around it has a pressure of 1,000 millibars too. Okay? An air parcel will always have a pressure that is the same as the pressure of the air around it. If it doesn't, it'll expand or contract, but we'll get there in just a little second. Now, let's say that we're going to lift this air parcel to some new height, okay, where the value of the pressure is lower. I'm not yet going to worry about how we're going to move this air parcel. As we're going to see later in this semester, there's lots of reasons why air parcels might change their height. Okay, we'll have a whole list of reasons actually. But let's say that there's going to be a way. We're going to lift that air parcel to some new height. Now at this new height here, let's say the air around the air parcel has a pressure of 750 millibars. Okay, we've lifted the air, I don't know, 750 millibars is a few kilometers above the ground. Okay, we've lifted this air parcel to some new height. Well, I'd like to say I could leave the air parcel at its original properties, that it has a pressure of 1,000 millibars, and it has a temperature of 30 degrees Celsius, but that can't be right. The air parcel can't have a different pressure than the air around it. It's going to need to have the same pressure as the air around it. It's not like it's in a jar where it can't expand or an air compressor or something like that. The air parcel will just expand. we'll get a bigger air parcel, right? It expanded until its pressure on its inside is the same as the pressure of the air around it. Important point. Rising air parcels always expand. Okay? Because, of course, always, as you lift the air parcel, the air around it will always have a lower pressure than it did before, because the air pressure always decreases as you go up. And therefore, the air parcel will always expand. But here's the deal. Expansion is work. You know, as my air parcel went from this side to this size, well, there was air in its way, right? This wasn't a vacuum between our old size of the air parcel and its new size. There's air in its way, and pushing that air out of its way is work. Work in the physics sense of the word, as in it takes energy to do it, okay? It takes energy to do the work of pushing the air out of the way. That causes the temperature of the air parcel to fall. Some of the energy of those molecules zipping around, remember, temperature is just the energy of the molecules zipping around. It's the kinetic energy of them moving around. Some of that energy is used to do the work of making the air parcel take up more space, of expanding it. Expanding an air parcel will cause the temperature of the air parcel to fall. So notice I changed my air parcel here. Instead of having a pressure of 1,000 millibars and a temperature of 30 degrees Celsius, I now have a pressure of 750 millibars and let's just say a temperature of 6 degrees Celsius. I'll be honest, I just sort of eyeballed that temperature. I didn't actually do the math and figure out what it would be. But an atmospheric science major certainly could. I mean, it's not a tremendously complicated calculation to do that. The air parcel will always expand as it rises, and it will always cool when it expands. Therefore, a rising air parcel always cools. We're not going to use the word always all that much in meteorology. There aren't that many things in meteorology that always happen, but here we got to use the word always a whole bunch. Rising air always expands. Expansion always causes cooling. Expansion always causes the temperature to fall. Rising air parcels always have their temperature falling. Man, we got to use cooling, the word always a lot. Anytime air expands, it cools. Hold on just a second here. I wasn't planning on this, but it caught my eye. I have one of these cans of compressed air in here for like, let's see if I can, for cleaning out my computer and stuff like that. This holds just compressed air. When I open up the valve, all it does is the air parcel that's in here is expanding out through the little straw and blowing dust. But here's the deal. As this air parcel expands, it's doing work. Doing work, pushing air out of its way. And as a consequence, the temperature of the container is falling. In fact, okay, so I'm holding it, doesn't feel all that cold yet. I'll go ahead and, these cans are like $1 or something, it's no big deal. Let's waste one. Alright, I'm blowing the air out of here. This air parcel is expanding. It's getting too cold to hold. In fact, I bet if I hold it a little longer, hold on. Maybe it's too dry today. I was hoping I could actually get it to be cold enough that it was colder than the dew point, and I'd start, oh, sure enough, it's getting wet. Look at that. I've actually cooled it far enough now that we've actually gotten the canister below the dew point temperature, and I'm getting saturation and I'm getting moisture on here. Making this air parcel expand is causing this to cool. Okay? It's an adiabatic temperature change. I didn't actually, have this can emit a bunch of radiation so that it cooled. No, it's an adiabatic temperature change. Just doing some work without removing any heat or anything like that has changed its temperature. Oh, that's cool. That worked out better than I was guessing. All right. Lifting the air parcel. They will always reach a lower pressure, they will always expand, and they will always cool. Let's do it further. Let's lift it a little bit farther up to maybe 500 millibars. Okay, to a pressure of 500 millibars, that's about 5 kilometers above the ground or something like that. And again, he'll have cooled even more. And so let's see here. I say that I have lifted it to 500 millibars, and now it has a temperature of like -24 Celsius. Again, I have to admit, I just faked these numbers. I didn't feel like doing the math. All right. Lifting air always causes temperatures to fall, which, by the way, tells us that if we do it the other way around, if we lowered the air parcel, it would always be warming. Lowering the air parcel is the opposite of lifting it. As we lower it, it will have a lower pressure than the air around it. Like if we lower the air parcel from 500 millibars to 750 millibars, Therefore, the air around it has a higher pressure than the air parcel does. It can crush the air parcel. Crushing is compressing the air, which causes the temperature to increase. The environment around the air parcel is doing work on the air parcel. That increases its temperature adiabatically. In fact, you can see we can go all the way down to the surface and get it even warmer. Sinking air parcels always get a higher air temperature. They always get a higher pressure. They are always being compressed. Let me tell you a little example about that there. Again, if we had an air compressor, I should have brought my air compressor up here, but if you have an air compressor, you turn it on, the thing starts doing work as it compresses air into the canister. You have to be careful when you use such a thing, but if you put your hand on it, it starts off, of course, at the temperature of the room, but very quickly, as the air compressor is doing work to compress air into the canister gets hot. Okay, very quickly it will burn you on that air compressor. Okay, just the opposite of how the canister here got colder as we let the air out. All right. So this air parcel, as we lift it, is cooling. We know that all air parcels will lift, as we lift them, will cool. And it turns out it happens at a fairly specific rate. Now, there's a condition on that, though. It depends on whether or not the air is saturated. If air is not saturated, if there's no condensation going on, if the relative humidity is less than 100%, if the temperature is greater than the dew point, all those good things there, it turns out to be a really nifty constant rate. The dry adiabatic lapse rate, or the dollar, D-A-L-R. And it's a constant. It's very, very, very close to 10 degrees Celsius per kilometer. It's like 9.98 or something. Degrees Celsius per kilometer. We'll use 10. Okay? That means for every kilometer we lift the air, the air temperature will decrease in temperature by, the air parcel will decrease in temperature by 10 degrees Celsius. Lifted 2 kilometers, it'll have decreased by 20 degrees Celsius. Lifted 3 kilometers, it'll have decreased by 30 degrees Celsius. Boy, that is handy. The dry adiabatic lapse rate, let's parse that name. Dry doesn't mean there's no water vapor in this, it just means that there's no condensation going on. Adiabatic, we're not worried about other ways in which the temperature might be changing, like our air parcel's giving off radiation or something like that, or it's experiencing conduction with the warm ground or something. No, we're not worried about any of that. This is just because of expansion of the air parcel. Lapse rate. We have seen that word lapse rate before. Lapse rate is how temperature changes with respect to height. And remember, if it's positive, we saw that back in the first module of the course. And remember, if it's positive, that means it gets colder as you go up. Now, this is a subtle point here. Keep in mind, the lapse rates that we saw before were like the measured lapse rate at 2 different heights. Like a weather balloon measured the temperature here, and then it measured the temperature here. But this air up here was different from this air up here. In fact, that's why we use the word environmental lapse rate. It was measuring the temperature of the environment at different heights. These dry adiabatic lapse rates, and we're going to have another one in just a little bit, are about as you move air. What was this air parcel's temperature here? What's its temperature once it gets here? That's a very different kind of problem. So the dry adiabatic lapse rate is the lapse rate as how temperature changes as the air rises if there's no condensation going on. What if there is condensation going on? What if our relative humidity is 100% or more? In other words, what if our temperature is equal to our dew point and all that good stuff? Alright, so here I have some air parcel sitting there at about 750 millibars, and let's lift this guy. But if he's saturated, well, that means that there's going to be condensation going on. But in the phase transitions of moisture lecture, we learned that condensation is a warming process. All those water vapor molecules have a lot of energy. And if they have to form liquid water droplets, they have to give that energy off so they can just sort of hang out in a liquid water droplet. There's a lot of latent heat being released by condensation. So in our air parcel, if the air parcel is saturated, if its relative humidity is 100% or more, if its temperature is equal to a dew point, all that good stuff, yes, as we lift the air, it is expanding and therefore is cooling by adiabatic temperature changes. But that's partially offset by the fact that we get all that condensation. And that condensation is giving off a lot of heat. In fact, what was it? 600 calories per gram of water that you condense out. And as a consequence, you end up with the so-called moist adiabatic lapse rate, or MALR, or MALR. Now, the moist adiabatic lapse rate isn't a constant, but it tends to be around 6 degrees Celsius per kilometer. And 6 degrees Celsius per kilometer is the value we'll use for the moist adiabatic lapse rate on like the homework set and so on, and the home quiz and so on, unless you're told otherwise. But it isn't exactly a constant, and I think a couple places in your book they use like 6.5 or 5.5 degrees Celsius per kilometer, but 6 is a good average. Moist adiabatic lapse rate. Moist in the sense that there is saturation, and we're changing water vapor into liquid water. Adiabatic, we're not worried about like radiation going on or conduction or anything like that. This is just due to the expansion of the air parcel, due to condensation, due to lifting it. And lapse rate, how the temperature is changing with respect to height. And because it's a positive number, that means that the moist adiabatic lapse rate is telling us that the temperature is still getting cooler with respect to height. As we are lifting this air parcel from like 750 millibars up to 500 millibars, we're lifting a certain number of kilometers. For every kilometer we lift it, it is cooling by 6 degrees Celsius. You could think of it as like it's actually cooling by like 10 degrees Celsius per kilometer, but then we're getting some of that heat back as we release latent heat from condensing out water vapor. Oh, all right. So let's make sure we can review these guys here. There's two different adiabatic temperature changes. Well, the dry adiabatic lapse rate and the moist adiabatic lapse rate. Both of them are due to as you lift air. As you lift the air will always cool. It's just which rate. If the air isn't saturated, you're going to lift it at the dry adiabatic lapse rate, which is 10 degrees Celsius per kilometer. If your air parcel is saturated, your air parcel is still cooling as you lift it, but not as much because you're getting some heat back in the form of that latent heat release as you condense water vapor back into liquid water droplets. So you get a moist adiabatic lapse rate of more like 6 degrees Celsius per kilometer. Either way, sinking air will always warm. As we lower the air parcel, it will always warm. And in fact, it will always warm at the dry adiabatic lapse rate. As we are warming the air as it sinks, it's only getting farther from being saturated. The relativity can only go down, so we definitely don't have to worry about latent heat release or anything like that. So as we lower the air parcel, it will always warm at our rate of 10 degrees Celsius per kilometer. Oh man. Now before we work through some classic examples of problems using that, let's go ahead and answer a couple quick questions. Question 4. A rising air parcel always has the same blank as the environmental air around it. Temperature, pressure, or density. What does their air parcel have compared to the air around it? Make a choice from those 3 options and get some feedback before you move on to question 5.